Start. The answer of question number 6 and 7 are almost similar. When ROH react with PX3, what happens? It forms ROH PX. Now, in case of PX3, this X minus acts as nucleophile, and this is leaving group. When this X minus attacks here, this X minus comes here and attacks here, it becomes RX and it becomes POH. Now keep in mind, in this case, SN2 type reaction takes place. Keep in mind, this is not although 100% true, but generally you can say that in case of PX3, the reaction will be SN2 type. And whenever we have reaction of SN2 type, there is no rearrangement. Therefore, and you know that SN1 reaction is better in case of primary, secondary, and it is poor in case of tertiary. And finally, you know that whenever you have to react with iodine, just you have to make or you have to prepare this as in situ. In situ means whenever you want to form PI3, just you have to react phosphorus with iodine, you will find that you are able to form. Now, question number 8. In question number 8, first I would like to discuss the reaction of SOCl2. See, what are the characteristics of SOCl2? First characteristic is the product is RCl plus SO2 plus HCl. These two are gas. Therefore, it is best method to prepare RCl. But there might be rearrangement. It means that in case of SOCl2, carbocation is formed and there is a possibility of rearrangement. There are two possibilities. If I write the mechanism, SOCl2, if SN2 is with pyridine, and the second case is if SO2 is without pyridine. When SL2 is with pyridine, then you have this product, inversion. When SOCl2 is without pyridine, then you have retention of configuration. What I mean to say, this is very important. Let us say this part. C at CS3, C2H5 and OH. When SOCl2 react with this, when SOCl2 react without pyridine, then just in place of OH we can replace Cl. But when it react with pyridine, it means that the position of Cl, if you draw the physical connection of this, you will find this is CS3. Now C2H5, Cl and H. In case of pyridine, it will be just opposite. Cl will come here, CH3 HN. In case of pyridine, we have backside attack. Yep, keep in mind. Next is question number B. I would like to explain why it happens. If you have pyridine, pyridine has this formula, and this is a base because it is electron rich. Now see what happens when ROH react with SOCl2. In first step, it loses HCl, ROHCl plus HCl. This is acid and pyridine is base. This HCl is trapped by pyridine and it forms this complex NHCl. This Cl minus attacks R from backside. That's why we have inverted product. If pyridine were not present, what will happen? When no pyridine is present, this Cl will attack this. Now, in this case, we have retention of configuration. What simply means that if you use pyridine, Cl will be attached from the side which is opposite to OH. If you don't use pyridine, Cl will attach to the side from which OH is leaving. That's the difference between these two. Now, we have B DOH SOCl2. As I told, in case of SOCl2, rearrangement is possible. If you remove this, what happens? Cation is formed, and this cation may rearrange like this. Therefore, there are two products possible. One from this the product will be DEA and Cl, and from this the product will be. So there are two products possible in case of it. Very important. Next we have D also. CH2OH HBr plus CH2OH2 plus leaves CH2 plus. This is 5-member ring. Here ring expansion takes place. And it becomes 6-member ring, and Br minus attacks. Therefore, this is the final product. This is also very important. Similarly, in case of G, you have HBr. This is lost. Now rearrange. We have minus. This is final because this was primary plus allylic. This cation is secondary plus allylic. Certain way it will rearrange to become more stroke. Similarly, in case of E, you can easily write the final product will be CHCl CH3. Now let us discuss question number 9. In case of question number 9, pH, CH double bond, CH, CH3, HBr.